So, dear students, I welcome you for the today's lecture related to the nozzle attachments reinforcement associated with the pressure vessel. So, we are going to understand what are the nozzles, where they are used, selection of nozzle location, type of nozzles, reinforcement, the types of reinforcement, and the designing of reinforcement. So, looking at this figure, the nozzles are there. To this vessel, this is a heat exchanger, kettle type heat exchanger, and to this, the different nozzles they are attached. This is one nozzle, this is another nozzle. In besides that, in this figure also you can see the various nozzles at the bottom. Even at the top, you can see the nozzles. There can be the nozzles attached to the side walls also. At this end, you can see one of the nozzle that is attached. So nozzles are attached to the different parts of the vessel. So nozzles actually look like this. The pipe that is there, and to that pipe a flange that is welded. Now, so this is a nozzle. This nozzle is to be attached to the vessel. So, nozzle is a device used to control the direction or characteristic of the fluid flow as it exists an enclosed head or enclosure. In other words, nozzles are provided in the process equipment for inlet, outlet of the process material, cooling or heating medium, for drains or vents, or for safety valves and rupture disc. Nozzles are located on the vessel according to the process requirement, and the nozzles can be either circular or elliptical in shape. So in general, what is nozzle? It is basically a pipe that is attached to the vessel for a certain specific purpose. So this purpose that can be the feed inlet, product outlet, or some utilities, or sometimes it can be the manways, or sometimes it can be for the safety purposes, sometimes for the instruments like your temperature, pressure measurements. These nozzles they can be located at any point in the vessel. They can be on the weld lines that the process engineer has to design the location, the number, and the dimensions of the nozzle. This all depends on the process requirement. The process decides where should be the location of a nozzle, how many number of nozzles they are required, what must be their dimensions, what is their diameter, which type of the nozzle I have to use. So all that will depend on the process requirement. So process engineer, a chemical engineer decides the type, diameter, location of the nozzle. Nozzles can be flanged or without flange depending on the type of the attachment. More number of nozzles incorporate the more cost. Now there are different types of the nozzles. Integral nozzle, formed nozzles, and fabricated nozzles. Nozzles can be either circular in shape or can be elliptical in shape also. Now the integral nozzle. So this is the one piece nozzle that is available. Now, as the name indicates, it is an integral part of the shell or a head. That is integral part of a shell or a head, and the portion of the head or shell by cutting and shaping is given in the contour of the nozzle, is given in the shape of a nozzle. That means it's a, for the vessel, if it's a shell, think of it as a shell, and I'm going to provide a certain hole here. This will be the integral part. It is only like that. It's an integral part and parcel where I'm going to cut it. A hole that is provided in this paper. So this will be the integral nozzle. The material should have the good ductility for this purpose. Not only that, it takes the connecting part of the nozzle and the shell, the integral forging also that can be done. At the same time, the thickness is increased by welding them with nozzle and shell. By welding them with the nozzle and with the shell. This is what the shell is and this is what the nozzle is. This is the integrally forged part that is available here. That is also the integral nozzle. And after that you are welding the nozzle component. Then there are the formed nozzles. Here generally the nozzle that is one piece of one metal. This can be fabricated according to the temperature, pressure of the process requirement. These are formed to the specific shape, size, either by rolling, forging, and then welding to the shell or the head. So basically, rolling and forging that is associated with this fabricated formed nozzles. Rolling is what? The two or more layers of different metals are thoroughly cleaned and then pressed one over the another, so that I am going to this one plate, I am putting the another plate and then rolling it thoroughly and then giving the desired shape of the nozzle. That is what the rolling and bending that is associated, rolling, bonding, and that is associated. Now the third is fabricated nozzle. These are the most common in the chemical process industries. Most common, where maximum is the fabricated nozzles. These are the short pipes or tubes fabricated from a metal sheet and are welded to the shell or head at the opening made in the vessel wall. So these are the most common vessel. You can see a pipe here, that is pipe is attached to the flange and it is attached to the vessel wall. So this is the fabricated nozzle. The length of the nozzle is 1 to 2 times the diameter of the nozzle. So this length is 2 times the 1 or 2 times the diameter of the nozzle. This is what the diameter of the nozzle is. So it is 1 to 2 times length. Then the nozzles, they can be where they can be attached. You can see in this figure, that is they can be radial or the hillside or tangential nozzles. tangential entry like in case of your cyclone separators. The stresses around the nozzle located in a cylindrical shell are not the same in all directions. You can see this CFD simulation where you can see the nozzle exerting the different stresses. So the red part that is related to the higher stress concentration. So these are the stress concentrated points. Nozzle present on the peak of a dish end do not disturb the symmetry of the vessel. Now this bottle that is there, its nozzle is in a symmetry. Now to this, if I am going to attach a pipe in this side, so its symmetry will be disturbed. So that is the location of a nozzle. I can attach one pipe here, I can put another nozzle in this section, another nozzle in this section, or I can put the nozzle in this section. So that is going to disturb the symmetry of the vessel and that is going to create a torque. So this is what the attachment of the nozzle that is also important. The nozzle present on the peak of a dish do not disturb the symmetry of the vessel, but present on the periphery of the pressure vessel disturbs the symmetry, result in the eccentricity which causes the stress concentration around the opening. Of cylindrical shell, circumferential stresses is 2 times the longitudinal stresses. So whenever there is a longitudinal direction, you can have the more circumferential direction, it will be the more stresses. The nozzle that cuts more material in the long direction has the higher stresses. In this figure, you can see the nozzle which is cut more material is having the higher stresses. This is the longer length that is cut, so you are having the higher stresses in this section. Nozzles with the reinforcement plate. Now in these two figures, you can see the extra additional plate that is attached to this basic shell, and this is called a reinforcement. This is called a reinforcement. So when the hole that is drilled in a vessel, that much portion of the vessel becomes weak when you are putting a hole. If the hole that is put and material is taken out in this portion, so the area around this hole that will become the weak because the discontinuity is observed. When you are taking out the material to make a hole, it becomes a discontinuous area. So as it's a discontinuous area, so it will be the weak area. So the area of the vessel wall removed is compensated by additional material. In the form of a metal sheet, this is what the additional material in the form of a metal sheet that is added. Actual diameter of the nozzle is this diameter of the pipe. However, this is what a reinforcing plate that is provided. Then as the stress concentration in the vicinity of the nozzle can be reduced by providing this extra thickness to the vessel wall or the nozzle. This stress concentration can also be reduced by providing the additional plate to the vessel wall or to the nozzle, that is called the reinforcement plate around the nozzle. Why that is required? To avoid the failure in the opening area, because it becomes a weak area. So there can be the possibility of failure. So to avoid the failure, you are putting this compensating ring or the reinforcing plate. The care to be taken as this additional compensation do not disturb the strain pattern existing in the vessel wall. That care has to be taken. Then reinforcement nozzle having the wall thickness larger has the minimum stress concentration in that area. Now you can see the nozzle that is attached to the vessel. Nozzle may be welded to the vessel wall at the periphery or may be penetrating inside the vessel. Now there are two figures. In this figure, the pipe, nozzle pipe that is attached up to the vessel shell up to the periphery only. However, in this second figure, it is penetrating inside the vessel. This nozzle pipe is penetrating inside the vessel. That means I am providing a certain extra length inside the vessel. That is also going to provide an additional support, additional strength when it is penetrating inside the vessel. This is to the periphery of the vessel. This is for the vessel shell. This is also the vessel shell. Vessel shell के अंदर inside वो nozzle गया हुआ है. This is only up to the vessel shell. This is inside the vessel shell. That is what? Penetrating inside the vessel. Then there is a balanced compensation and unbalanced compensation. The compensating material plate is provided on both the sides of the vessel wall. The compensating material or reinforcing plate is provided on the both the sides of the vessel wall, and the unbalanced compensation, the compensating material plate is provided either on inside or on outside of the vessel wall. Again, in this figure, this is the additional plate, reinforcing pad, or the additional material that is provided on the outside of the vessel shell. Outside of the vessel shell. So it becomes an unbalanced compensation. If this reinforcing pad that is on both the sides of the shell, that means it is on the outside as well as on the inside, of this vessel shell, then it will become a balanced compensation. So unbalanced may either on the outer side or on the inner side. And in balanced compensation, the reinforcing pad or reinforcing plate is on the both the sides of the vessel shell, that is means inside the shell as well as outside the shell. Then there is integrally reinforced nozzles, means one pipe forged nozzles. Integral reinforcement can be achieved by excess material in the shell. Excess material in the shell or the nozzle or the combination of both. That means the reinforcing material, I can provide the reinforcing pad, or I can provide the higher thicknesses for the nozzle and higher thicknesses for the shell. So a thick insert plate on the shell also qualifies. It doesn't matter how many parts it may be. Now in this figure, the different areas that are shown, you have to simply understand the areas are there. So this is what the actual hole, but A is the actual hole, that area is there. However, the nozzle diameter that is cut is this area plus this thickness of the pipe that is also added. This is what the actually it is cut. Then the yellow A1, that is what the reinforcing has been added. Now there are different methods for the reinforcement. The area for area method, that is the most common in chemical industries. Area for area method means how much amount of the area that has been taken out, the same amount of the area that is to be provided as a reinforcement, so that the weak area that will be compensated. So looking at this figure, the extra, this is what the shell is, the nozzle pipe, this is protruded inside the shell, outside the shell that is also there, and the reinforcing plate will be provided in this section on both the sides. So the maximum horizontal distance KL, which is equal to 2 times the DN. This KL is 2 times the diameter of the nozzle DN. Then this is what the safe compensation limit. Then maximum vertical distance. This Km is the maximum vertical distance. Km, which is equal to 6 times the shell thickness. Ts is the shell thickness. Into bracket 3.5 times the shell thickness plus 2.5 times the nozzle thickness. The theoretical thickness of a shell without considering corrosion and excess, based on external pressure only. Ts is the based on the external pressure only. Then the required compensation for the nozzle to be rated at the maximum allowable working pressure P. So theoretically calculated thickness of a shell. What is the theoretical calculated of a shell thickness? So that is calculated as TRS, which is equal to PdS upon 2Fj plus P. It is what general formula we are going to calculate the thickness of a shell. Similarly, the thickness of a nozzle, that is also calculated. Then the actually used is something different. You have done some calculations, right? You are adding the certain corrosion allowance. You are going to do the certain round off. So it is the more thickness, and round off, that is also going to add the thickness. So actual thickness is something different, and theoretically required or calculated thickness is different. So actual thickness used is always higher than the theoretically calculated thickness. That means the theoretically calculated thickness, you are adding the corrosion allowance, you are adding the round off, that is added. So Ts is the actual thickness that is used. Ts is the actual thickness of the nozzle, and Ts1 is the thickness of nozzle without corrosion allowance. That is what? Nothing but it round off. So Ts1 is equal to Ts actual thickness minus theoretically calculated minus the corrosion allowance. So you will get the round off or added thicknesses. So this is the extra thickness which is already provided by the shell. Similarly, the extra thickness that will be provided in case of the round off by the nozzle, this will act in compensation. This is the area by area method. So area of the nozzle, which is equal to pi dn into t. Area of the nozzle, which is pi dn into the t. The thickness provided in excess while fabrication is given by. Now the required compensation for the nozzle to be rated at maximum allowable working pressure, and AR is the required area. Now this is AR, which is equal to dn minus 2 times the thickness into the thickness of the shell. This is the thickness of the nozzle. This is the thickness of a shell. dn minus 2 times tn means dn minus 2 times the thickness of the nozzle, tn. This is the tn, dn minus 2 tn. So the actual hole available, this is what? The actual available hole for the fluid flow multiplied by the theoretically required shell thickness. This is what? Actual area for the compensation. That much amount of the area that is actually removed. So area into the thickness. Now the area already available in excess. Excess metal thickness available with this shell. We have already talked. TS1, that is the thickness of a nozzle without corrosion allowance. This is what? The excess thickness which is already available. So this TS1 and TN1, that will already available. So excess metal thickness available with this shell or head, that is A1, which is equal to dn into TS1, which is nothing but TS minus TS1 minus C, TRS. This is TRS minus C. This is TRN minus C. This is the portion of the nozzle external to the shell or head. Now there is a portion of the nozzle inside the shell or the head. That means which is protruding inside the vessel. Which is protruding inside the vessel. That is also acts as an additional part. So this is the A3, which is equal to 2 times the Ln2 into the thickness of the nozzle minus 2 times the corrosion allowance. Why 2 times the corrosion allowance? Because on both the sides you are having the exposure of the fluid that may corrode. While we are taking into account the upper section, there is only on the one side corrosion. However, this internal portion, that is exposed for both the sides corrosion. So that is what? It becomes 2 times the corrosion. Then the additional compensation required, that will be equals to AR minus already available compensation. A1, A2 and A3, they are already available compensations. and AR is what is actually required. So AR minus already available compensations. Already available compensations, one is from a metal thickness available with the shell. Second, metal thickness available with the nozzle. And the third, that is the nozzle inside the shell. So this is what already provided compensation. So actually required and already provided. Whatever the difference is there, that will be provided for the compensation. So additional plate of the remaining area, that is be used as a reinforcing plate. This compensation is provided by compensation ring, which is welded to the periphery of the nozzle. If the nozzles, they are not properly reinforced or not provided with the proper compensation, then such type of the accidents that may takes place. The buckling of the vessel that can takes place only because of the improper reinforcement. So these are the different reasons by which the failure of the nozzles that can takes place. So this is all related to the nozzle.